we're going to take a few minutes to use these slides to help prepare for the barium hydroxide sulfuric acid titration and stoichiometry lab. This goes back to what we do in first year chemistry when we dropwise titrate with hydrochloric acid and sodium hydroxide. And we've got hydrochloric acid and sodium hydroxide, same molarity, and we just use little barrel pipettes to add a certain number, and we're going to talk about 5 drops here, of HCl into distilled water, and then we usually add phenolphthalein, see a color change, and then drop by drop we add sodium hydroxide to see what the conductivity does as it happens and maybe explain it on a molecular level. So, this is the conductivity curve that results. As you can see, we're adding 1, 2, 3, 4, 5, 6, 7, 8 drops of sodium hydroxide to the hydrochloric acid in a beaker. We stir after every addition and we see what happens. We get the sodium hydroxide turning the solution pink around here. So this is what the first year lab students do. Now, we then add a best fit line, 2 lines actually, to first of all this decreasing concentration versus drops, and then to this increasing, we see an increasing conductivity. And we write down the full equation. You might want to write the net ionic equation that you can derive from this very easily. And when each hydroxide ion is added, it's reacted with hydrogen ion. And you can see that here is your net ionic equation. So this takes the hydrogen ion out of the conductivity stream. Remember, a electric current is taken from moving charged particles, so we can measure it, and that's a measure of the number of charged particles that are available to pass the current. So this takes hydrogen ions out and leaves sodium ions in. And we think about this in terms of just 5 pairs. It makes it a whole lot easier to think about, although we know there's millions of ions involved. So 5 pairs of ions, and we say there's 1 ion in each drop. That's ludicrous, I know, but it makes the diagram a whole lot easier to draw. So we start with hydrochloric acid, hydrogen ions, and the big chloride ions floating around surrounded by water. We introduce 1 drop of sodium hydroxide, which immediately is already dissolved in water, and they're very motile, so the hydroxide scarfs up a hydrogen ion and leaves the sodium ion, which is larger. We change the hydrogen ion, which is very small, very light, into water. The bulkier sodium plus ion is substituted for it, and that's of course 23 times larger, and so the big sodium ion moves more slowly than the little hydrogen ion, and the conductivity drops a notch. When we add the second drop of sodium hydroxide, the same thing happens, forming another water, another sodium ion is left behind, the conductivity drops. And then that goes on until all the hydrogen ions have been replaced by sodium ions. And that means in each one of those additions, the conductivity has dropped, because there's the same number of ions, cations involved, yes, but they're bigger and slower. The next drop of sodium hydroxide, however, introduces 2 new ions, and the hydroxide looks around for a hydrogen ion to neutralize it, doesn't find it. So now we've got the hydrogen ion and the hydroxide ion running wild in the solution. Conductivity rises dramatically with the addition of each of those sodium hydroxides, and that's what gives this positive slope straight line. We add the best fit lines. We then find the equivalence point here from the intersection point of the two straight lines, and that's the volume of sodium hydroxide that would have exactly neutralized the acid. It's about 4.5 drops. So then we used that volume in the equation to find the molarity of the acid. We started off knowing the molarity of the sodium hydroxide, and here's the volume of sodium hydroxide that is then added. We started off knowing there were exactly 5 drops of hydrochloric acid, and so we solved this equation for the molarity of the acid, the volume of base times molarity of the base divided by the volume of the acid, and we now have calculated the molarity of the acid. This is a very critical type of experiment we're going to use as we treat the barium hydroxide and sulfuric acid, and the sulfuric acid is added to the barium hydroxide to form barium sulfate.